Hello everyone, I want to inform you guys Johnson's algorithm today. Johnson's algorithm is a way to find the shortest path between all pairs of verticals in an edge-weighted direct graph. As we know, there are two main ways to find the shortest path between nodes in a graph. There are Dijkstra's algorithm and a Bellman-Fold algorithm. Comparing to the Bellman-Fold algorithm, although Dijkstra's algorithm is much more efficient, it is not capable of handling graphs in which some of the edge weights are negative numbers. The Johnson's algorithm is an important way to change weights in a graph so that we can make the graph satisfy the standard of use Dijkstra's algorithm. Okay, let's start to inform it. I will give you guys an example to help you understand it. Here's an edge-weighted direct graph G. We say there are some edges with negative weights in this graph so that we can't use Dijkstra's algorithm to find the shortest path. Johnson's algorithm uses the technique of reweighting. For reweighting, we need to add a new node S to the graph, connect by zero-weight edges to each of the nodes. Because this new vertex has no edges to go into the graph, it's sufficiently invisible from the perspective of all the original vertex in graph G. So, in particular, the shortest path distance between any pair of U and V in the original graph is unchanged by this addition of the vertices. We can conclude that adding S does not any new path for graph. And then the Bellman-Fold algorithm is used because there are some negative weights edges in the graph. Starting from the new vertex S to find for each vertex V the minimum weight HV of a path from to S to V. The path from S to other vertices can't be worse than 0 because we assume that paths S to other vertex are 0. Here are the shortest paths. We have added values in each vertex of original graph which I used green to mark. For the next step, we need to redraw the graph and we need to move the S out. We can use the function which is omega prime uv equals omega uv plus hu minus hv to figure out the new weight of edge. Because this video is to inform Johnson's algorithm, we don't pay attention to prove the function. Omega uv is the original weight of edge. Hu and hv are the beginning and end of vertex for the edge. So we can compute the new weight of omega uv. For edge BA, omega uv equals 3, hu equals 0, hv equals -1. So the new weight of edge omega prime uv equals 4. According to this, we can reweight all weights of edges. I mark the new weights with red. After that, all the edges in the original graph have been changed to non-native. Therefore, the graph satisfies the conditions to use Dijkstra's algorithm to find the shortest paths between all pairs of verticals in an edge-weighted direct graph. However, how to get the results for the original weights of edges in the graph? In other words, how we change the numbers of results to what we want. As we mentioned before, here is a function omega prime uv equals omega uv plus hu minus hv. Maybe we can transform it. When we use Dijkstra's algorithms for finding all shortest paths for A, here is the results. Let's repeat the progress of transform. Delta uv plus hv minus hu. The delta uv is the value of the path between vertices so that we can get the results we want. For A to B, delta prime uv equals 2, hv equals -1, which is the value of passes S to B we mentioned before and we marked as green. Hu equals 0. we can get the value of pass of A to B is 1 for A. Other passes are also easy to compute. According to this, we can transform all the results to what we want and return. Now let's talk about complexity. Because we use both Bellman-Fold algorithm and a Dijkstra's algorithm, the time complexity of them are OVE and OV log V. In the Johnson's algorithm, Bellman-Fold algorithm called once and a Dijkstra's algorithm called V times, so that the time complexity is O V squared log V plus VE. The worst case for it is O cubed plus VE, as Dijkstra's algorithm takes O n squared. As we see, the time Johnson's algorithm costs according to number of edges. The biggest number of edges for a graph with n vertices is n multiply n minus 1. The time complexity will become big and not efficient under this situation. Fine, we inform the Johnson's algorithm from three aspects: the algorithm description, time complexity, and the limitation. Johnson's algorithm is a useful algorithm. I hope my video can help you a lot. Thank you for watching.